C, D, and E, plus all of number 2, 3, and 4. We just made that probability distribution table. And a good way to check to see if we got all the probabilities correct is actually to look at question C. In this case, since it's out of 36, we know that if we add all those together, 3, 10, 7, 8, 5, 2, and 1, it should add up to a total of 36 out of 36. If you did yours at home and it added up to, say, 33 out of 36, or your total was 33 or 34, or even if your total was more, like 40 or 39, it lets you know you counted something wrong. Is this always the case? Yes. This is an excellent way to check to see if our probability distribution table was correct, to see if it adds up to 36 out of 36, or to make sure it adds up to 100%. D says, what's the probability that the sum is greater than 4? Well, that means either a 5 or a 6 or a 7 or an 8. So we add those probabilities together. We get a total of 16 out of 36. What's the probability that the sum is 3 or an even number? Well, 3 is 10 out of 36. Plus, we had to add all our even number probabilities. So our probability for a 2, a 4, a 6, and an 8 as a sum. I think there are 16 even squares. So for the rest of E, we get 26 out of 36. I like question 2. We have to thoroughly explain what it means for two events to be mutually exclusive. Draw a Venn diagram to represent two events that are mutually exclusive. So I'm going to pick something that's mutually exclusive. Event A. We're going to call event A being in high school. Event B, sorry, that's event A. Event B, we're going to call event B being in middle school. Now maybe there's a special case I'm not aware of, but I'm pretty sure all of our high school students are not in the middle school, and all of our middle school students are not in the high school, that nobody is in the 8th and a half grade. We have to draw a Venn diagram, so that's our circles. So for DSA, we have our middle school students and our high school students. And notice there's no overlap between them. Everybody that's in the middle school category is completely separate or excluded from everybody in the high school category, right? And we still need a good explanation here. So our explanation for this is, if event A occurs, event B cannot occur. Or we could reverse that. If event B occurs, that guarantees event A will not occur. If we pick somebody that's in high school, it guarantees we do not pick somebody in the middle school. Or if we pick a student at random in the middle school, it's going to guarantee they're not in the high school. Okay. The addition rule, so the probability that you pick one or the other. Well, for mutually exclusive events, we have the probability of A plus the probability of B. And that's actually what we were using up here. We were taking the probabilities for different categories and adding them together to get the probability of getting a certain combination. Like that question, what is the probability that the sum is greater than 4? We could rephrase that as, what is the probability that the sum is a 5, a 6, a 7, or an 8? Well, we just added up all of our probabilities to get our probability for or. One thing we want to add, though, is that since it's not specified anywhere else, we need to subtract the probability of A and B. So if there is overlap, if you have something that is not mutually exclusive, where someone can, what we call in class, double vote or be counted twice, you need to subtract everybody that's counted twice. And if you're curious what that means, let's go ahead and just do number 4, because number 4 is going to have some of this going on. We know that 45% of Americans own a dog, and we know that 34% own a cat, and then 20% own both. So there are some people that counted as dog owners, and there are some people that counted as cat owners. They were overlapped, right? It wasn't just all the dog people and all the cat people separate. This was a case where dog people and cat people have some overlap, right? There's these people that own both. They're in both categories. So this would be a good Venn diagram for non-mutually exclusive scenarios. Are these mutually exclusive? Why or why not? No. Owning a dog does not prevent you from owning a cat. If I pick somebody at random and they own a dog, there's still a good chance they own a cat. Or if I pick somebody at random that owns a cat, there's still a good chance they own a dog. So they're not mutually exclusive. Find the probability that a randomly selected American owns a dog or a cat. Well, that's going to use our multiplication rule for or. The probability is going to be, well, we got our dog owners, that's 45 out of every 100 people, or 45%, plus our cat owners, plus our P of B, so that's 34 out of 100. And then some people were counted in both categories, specifically 20%, 20 people, or 20 out of 100, were counted in the cat category and the dog category, so we got to subtract those double voters. And I think we get 59 out of 100 as a total. All right. So that's the rest of page 1. The main thing, besides just finishing up that probability distribution problem, was this idea of what is mutually exclusive, and then also how does it affect calculating probability for probability A or probability B. I really should squeeze in that this answer right here needed to start the probability of A or B equals, and then this is the calculation. So if you've got some space, make sure your row says probability of A or B equals probability A plus probability B minus the probability of A and B minus the people that are counted twice. All right, go ahead and click the next video for the two-way frequency table.